just get started this section and talk about the definition of vector. In math physics, we have a slightly longer, more complete definition or treatment of tensor. But this is kind of the first, a little simplified way of defining tensor. And what we try to do is to introduce the concept of pseudo tensor or pseudo vector. Now, according to this transformation property, because up to here we don't mention that the difference nature of like the electric field and magnetic field. But when we talk about this transformation property, actually one is electric field is a vector, and then the magnetic field is pseudo vector. And so we see how far we can get in a few minutes. Now, we'll probably just some definition of what we try to do. So basically, we are expressing physical law using vector, and like electric field or sometimes magnetic field, we still call it vector, right, for now, and then other quantity like position vector, and you have the velocity vector. And one of the main assumption in physics is that this thing exists objectively. So like a vector, like a velocity vector exists, whatever we try to describe it. But to describe vector, sometimes it's hard to just talk about an abstract vector with any numerical reference or numerical representation. So much easier to represent a vector using a coordinate system than we just talk about their component, say vector in three-dimensional space. We have three numbers to represent them. You can choose rectangular coordinate or other coordinate system. But we stay with rectangular coordinate, and there's still a freedom because like you have x, y, z coordinate. You can use this coordinate system to represent a vector, and you can translate the vector to the center, whatever the center. And we can stay with the position vector first. If a position vector, you starting from the origins, and don't confuse that with the coordinate is x vector, right? So if this go in the physical law, we require that this is objectively exists. What it means is that although it's original in this system, we represent it with using three coordinates, right? But this is your artificial choice. You choose the coordinate system, so that is man-made, not the nature. The X is existent in nature. So therefore, what we want to do is to make sure that this exists in nature, independent of the choice of your coordinate system. In particular, this coordinate system, although it's rectangular, and we define the scale along x, y, z are the same, but by keeping all this the same scale along x, y, z, we can still rotate the coordinate system. So rotate it to x prime, y prime, z prime. Right, we can do a rotation in space, and all that will the vector in the new coordinate system become x prime, y prime, z prime. Right, you have three set of number, and so this new coordinate and the old coordinate will relate to each other by transformation, what we call the transformation matrix. Jackson's notation. X alpha is 1, 2, 3, alpha 1, 1, 2, 3, and then x prime is given by this. Jackson first keep this summation. Later on, sometimes we'll get rid of the summation and use the Einstein notation, you have the matrix A sub alpha beta multiplied by this coordinate x beta. Okay, they basically sum over beta, and in Einstein notation, you have repeated index, then it means sum. Okay, so that you can do that. All right. So this is just like a matrix multiplication. If you go back to this, represent this as a column vector, x prime, y prime, z prime is equals to this A matrix multiplied by x, y, z. The O coordinate x, y, z, which is this x beta, multiplied by this matrix, which is A11, A2, A1c, A22, A23, A23. You're basically doing this summation A this times that, plus this times that, plus this times that, go into the new x prime, right? And so on, right? So that is a transformation matrix. And we specifically require that when you rotate, you keep the origin. So this means this linear transformation. Yeah, linear in x, get linear in pi. You don't consider this translation yet. And sometimes you consider translation, but in this consideration, how we define a vector or tensor, we're staying with the linear transformation. And now to define a vector or tensor, it becomes how you look at the property of this transformation matrix. But we'll talk about that next time, right? And finally, this again, this is a simplified notation. We are writing everything in subscript, but in the tensor chapter in math physics, you will learn about that. We define different kind of vector. One is what we call covariant vector, the other contravariant vector. One is put instead of subscript, put it in the index in the superscript. Then sum over subscript and superscript. But in this chapter, Jackson's treatment doesn't differentiate that. We're just using a, because we want to, the main thing we want to discuss is the difference between vector and pseudo vector, tensor and pseudo tensor. So that's not a full tensor treatment yet. Okay, but we'll look at the property of transformation matrix next time. So you have originally you have XYZ coordinate. We are dealing with just three-dimensional space in simplified treatment, because in tensor you can any dimension is fine. But for us it's just three-dimensional, and then the main idea is that a vector exists independent of coordinate. Coordinate is your choice. So you rotate it. Just deal with rotation now, keeping the origin, so we have no translation. Change the x prime, y prime, z prime coordinate. Right, you still have the same vector. So the vector is the component in x, y, z will transform to x prime, y prime, z prime, in something like a matrix. So this is Jackson's notation. So we have pi alpha equals to some A alpha beta, and then x beta. Last time I mentioned that we not differentiate what we call the covariant and contravariant vector. We're just using subscript all the way. And then Jackson add the summation of beta, but to save some writing, you just use the Einstein notation starting from now. Just whenever you see a repeated indices, it means it's sum over. So there's a sum over beta from 1 to 3. 1 We use 1, 2, 3 instead of XYZ just for convenience of summing over XYZ, summing over 1, 2, 3. Okay, so that's a transformation matrix. And then in order to say that the vector has something independent of your choice of coordinate, then we require some constraint. The constraint is that the length of the vector is invariant. So whatever your choice of the coordinate system, the length of the vector doesn't change. And for Cartesian coordinate, the length of the vector is just sum over the square. Right? So basically, now you need to explicitly sum, so like sum over alpha x alpha pi square, because we don't have a repeated index, or you can write x pi alpha x pi. That's that you can ignore the sum. But if you write it as square, you add explicitly the sum. Okay, so then it should be equals to x betas, or you can say whatever. This is sum over indices anyway. So whatever index, this is just a summation index, so it doesn't matter, right? Whether x alpha or x beta, right? Then you can use the substitute this transformation into here. Then obviously the first one, x alpha, is just the same, x alpha beta, x beta, right? That's just one of them. The other is sum over alpha, and so you have another alpha. But then you cannot use the same beta because you already sum over this. For the second one, you use another index, another label, like gamma. It's actually using gamma. It doesn't really mean gamma, right? So in order that this is equals to that one, then it must be this equals to that. This implies that the sum over these two is a conical delta x alpha beta. A alpha is conical delta. That only when this is true, then you can change one of them. Because of the conical delta, you can change gamma to delta here, then this becomes x beta. And so this would be equals to, I mean, this is whatever you call it, alpha and beta, doesn't matter. Like when this is true, then this one will go back to this one because of the conical delta. Sum over this two becomes this delta function, conical delta, and sum over either beta or gamma. Using the conical delta, just change the other index to say sum over gamma, so you change gamma to beta and get to this one. Okay, so that's the property of the transformation matrix must satisfy this one. This satisfies by this rotational matrix, and the rotational matrix, of course, you can look that up, or figure that out. Whatever the geometry define how you rotate. Usually, you need to rotate 2 times, so at least 2 angles. But sometimes people use 3 angles. But anyway, as long as you specify how you rotate, then this is fixed. But it must satisfy this relation. And this relation, you can put it in the other way. Say, this is sum over alpha, right? You can, like, changing the order of this index. And this procedure, we call it just a transpose. This one equals to this A alpha beta element is equals to the beta alpha element of the transpose matrix. Okay, just basically interchanging row and column. This is called a transpose. But then this would be in a form like a matrix multiplication. So that's still displayed. So this is index form, but in matrix form, it means that this A matrix, the transpose of this matrix times the matrix itself. And this matrix conjugate delta is just identity. The transpose times itself equals to the identity matrix. This is called, for real matrices, that's this relation defined what we call the orthogonal matrix. Okay, this is orthogonal. If this is a complex, then one of them is a complex conjugate. Then this is called unitary. In math physics, you have more of that. Or you might have learned about this before. Okay, so.
But how can you transpose just one of the matrix? If you transpose all the
transpose means interchange column and row. So like you write explicitly, say, because this is just three dimensions. It's easy. It's A11, A12, A13, A21, A22, A23, A31, A32, A33. The transpose will be just interchange row and column. So this becomes this row becomes a column. One, two, one, two. Okay, this is a transpose. The transpose will be like that.
But as per this equation, the A alpha beta is equal to the transpose of A.
This equals that? No. You interchange the indices. I interchange the indices. This is alpha beta. This is beta alpha. Okay, this equals to that, which is said by definition. By definition, in index form, the transpose is just mean you exchange the indices. Okay, and then the transpose, like alpha beta is 1, 1, 2. This 1, 2 is this one, right? And now this one will be equal to the 2, 1 element, which is this element. So that is exactly right. This is just the definition of time. Okay. But this is not. This is a special property of a matrix. If you satisfy this one, that is what we call the orthogonal matrix. Okay. And now another property is that the determinant of the transpose and the determinant of the original matrix is the same. So you take a determinant of the left-hand side and right-hand side, then you see that this implied determinant of A square, a determinant of identity matrix obviously. So that the determinant square of A, the transformation matrix must equal to 1. So there are two possibilities. Determinant A can be 1 or minus 1. Okay. If it is 1, this is sort of a Popper transformation or Popper rotation. Okay. Then when this minus 1 is not Popper, what they say improper, whatever. Jackson call it. Did he say that? Popper rotation, and then minus 1 is how do you say it? Is it improper or non-proper? So this is not proper. Okay, this is proper. This is not proper. Okay, so proper rotation means it's just ordinary rotation. If you keep rotating x, y, z, then however you rotate, the determinant will still be 1. And the transformation matrix having the -1 means you know, in addition to rotation, you do one more operation that usually involve an inversion of one of the coordinate. If this is x, we change the minus x1 or extend the x-axis the other way around. So instead of pointing this way, pointing the opposite way. That in that case, obviously you learn about it. If x, y, z originally you call this a right-hand coordinate system, then you invert one of them, then this becomes a left-hand coordinate system, and that will make the determinant -1. Another situation is you invert all of them to x, y pies, z pies. Okay, and that is also will give you a determinant of 1. You invert 2 of them, obviously, you go back to the right-hand coordinate system, and that is equivalent to a rotation. You can show that you can rotate equivalent to inversion of 2 of the axis. So that doesn't change the determinant, it's still 1. Okay, so we need to separate these two cases. And the idea is you want to show that, I mean, originally people will assume that when you invert the space, it doesn't matter, whatever left-hand or right-hand coordinate system, you still describe the same thing, then the physical laws should remain the same. So you want to show that the world inside a mirror is the same, satisfy the same set of physical law as the world original law. Well, that is, people thought that this is true, for a long time, until one time that people talk about this weak interaction with the so-called beta decay. That is not satisfied unless you make additional change. If you don't do that, then the physical law just differentiate the left hand and right hand. The world inside the mirror is different from the outside world. So the next step, the additional need to change is basically changing also whether the particle is ordinary particle or anti-particle. You change the anti-particle, things will become correct again. All right, but before we talk about that, we just need to separate the transformation. And some vector, ordinary vector like the position vector, obviously we already mentioned that. And they transform by rotation, and the transformation is according to this rule. And we can extend that from vector to tensor also. Say if you have a tensor, whatever the tensor alpha, beta. If it is in the pi encoded after you do the transformation from the original coordinate, A, now alpha gamma, A, beta, delta, B, gamma, delta. You have to satisfy this kind of transformation. Because you have two indices, you need two transformation matrices to transform. And if a quantity satisfies this transformation, this is a tensor. If it doesn't satisfy, it's not a tensor. Okay, and so that is that. Likewise, this is position, but any vector satisfy this is still a vector. We already use A. So B, any vector, A, alpha, beta. This is pi, B, beta. If we satisfy that, it will be also a vector. like the position vector. Okay, so but then we'll see that there are other object that is not transformed exactly like that. It's transformed like that times the determinant of this transformation matrix, what you call it A. Okay, if it transforms like that, that's become the pseudo vector. And likewise, if it multiplied by determinant A is a pseudo tensor. Now that you can treat it as a definition, but you can actually go a little further. But that a little further requires some math, so that may be a little difficult. So stay with me a little bit. So we will look at the explicit example of a pseudo. Say that again.
For this to be a pseudo vector, should A be a vector?
This is a transformation matrix. This is transformation. This is I use A as this transformation matrix. Okay. So if it transforms like that with this determinant A factor, then this is a pseudo vector. If you don't have that factor, extra factor, this is a vector. So you need to differentiate the two. Okay. And especially like you have this inversion, a spatial inversion, then you have the extra -1 in the determinant factor. Like we'll look at some example if you want, but let's stay with the what we try to do. Give an example of a pseudo vector, explicit example of pseudo vector, and so we need some space because that would take some writing. Okay, so yeah, learn about all this one. So one example is like the cross product, say, of vector, cross product of two vectors. Well, no, I'm using A as a vector. The transformation matrix is A as a tensor, as a second rank tensor or matrix. Right. A plus B. Just stay with this symbol. Okay. And so if A and B are all are vector, then C will be a pseudo vector, and we'll try to show that. I think I'm following Jackson. Oh yeah, Jackson is the other way around. So let's follow Jackson. A is B plus C. Okay, it doesn't matter whatever you call it, but now we will show that, try to show that, hopefully you can follow. And the idea is much easier to use the index form, so like A alpha component is now you introduce this epsilon alpha beta gamma beta gamma. This epsilon, you learn about all this, right? The epsilon, the Levi Civitan symbol. Have you? Everyone is okay with this? Okay. You learn about this. This is a so-called anti-symmetric. This is a third rank tensor. It's actually a pseudo tensor. Later on, we'll show that it's a pseudo tensor, but it's third rank. And well, we'll learn more about that later. But first, we'll just use this as a starting point. Okay, so that is how you express a cross product in index form. Now we want to transform that. You want to transform that according to the transformation property of beta and gamma, right? And the idea is you can define like a. At first, if you're not treating it as you treat it as like a label or a tensor or just some kind of operation. So you're not transforming this, you're only transforming this first. But later on, you identify this actually is like a tensor, actually a pseudo tensor. So you transform A prime according to how you transform B and C. So you have epsilon, alpha, beta. So you're not transforming this one, assuming this is just what you define as an object with some indices. Okay, and now this transform like a ordinary transformation matrix. Say like this is beta, right? Transform like a not yeah the transformation matrix. So it's A beta, we already use gamma, delta, and B delta. Right. So transform B to this one and transform C to A gamma, whatever, like using delta epsilon, C epsilon. Okay. Now now you have already have two of them, two of these transformation matrix. Actually, we'll do a trick. We'll do a trick that adding two more because we already learn about the property of a transformation matrix, A alpha gamma, A alpha delta, delta. We have too many delta gamma. Then we want to add two more of this into this object. I mean, Jackson just wrote it down in 6.147, didn't explain that. I'll try to get to this. Basically, well, that's more than one way to do it, but I'll add, say, like change the first index of this one. So this one, this is alpha is following this alpha. It's sum over beta, sum over gamma, sum over delta, sum over epsilon. Now we add another sum, and alpha instead of just alpha, you can see is alpha prime, beta gamma, delta alpha prime. You sum over alpha prime, you get back to alpha. Beta delta. A gamma epsilon. B delta C epsilon. This is interchangeable. You can change the order of your product. That is fine. After you do the index, that is fine. Okay, and now using this one, epsilon prime, epsilon alpha prime, epsilon alpha prime. And this is like introduce two more. So you have an alpha prime is you have A alpha something because this alpha is the second index. This is a delta. This is a conical delta. So you need to sum over another index. We already use up to epsilon. What is after epsilon? Yeah. Well, let's make up one. Make mu alpha a mu alpha pi, and then two more a beta delta a delta delta c epsilon. Now altogether you have 4 of them. Now what we want is just keep 3 of them grouping together. Basically, the 3 of them you have alpha pi, beta, gamma. Use the another property that you actually sum over that is also true. Alpha delta a delta alpha. You sum over the second index, it's still the same. Right. So that make it a little easier. So I just want to interchange that alpha mu alpha prime mu. Okay, so that is more like it. So this will become a alpha mu, and now you group the other 3 epsilon alpha pi beta gamma a alpha pi mu a beta delta a gamma epsilon. So you have this object, and then you have the rest is just b delta c epsilon. Okay, so so now the part that will give you the determinant is that this is equals to, this bracket is equals to a epsilon, the second index mu delta epsilon, the determinant of the A matrix of this A matrix. Okay, and for this one, for this relationship is a general relationship for any matrix. This is not just restricted to the transformation matrix. It's a little bit. It takes a little bit of thinking. So the determinant is basically, if you know another way to define determinant other than other than the usual ones, or using a matrix to determine, at least for 3-dimensional space, for a matrix determinant of any matrix A is defined by just sum over all possible. That's basically sum over epsilon alpha beta gamma, and then following the correct ones, 1 alpha, 2 beta, 3 gamma. If you have a 3-dimensional space, and then this index is going to 1, 2, 3, and then the determinant of a matrix that is the product of 3 elements, and they always take from one from the first column, the other is from the second column, and the third one from the third column. Say, if you remember, A matrix is 1, 2, 3. I mean, this index is the rows. It's the same as always taking one element from each row or each column. But there's a sign. if you're taking like the second index, if it is follow the rotation, the cyclic rotation of 1, 2, 3, then it's a positive sign, just like the epsilon. If it's one of them is reversed, then it's the negative sign, just like that. If you sum over all of them, all possibility, then you get the determinant. If you have repeated index, which means the two column, two row are the same, if like alpha and beta is the same, then this will be 0, because this epsilon is also 0. So if you have epsilon alpha alpha, gamma is 0. So you have two, if you have two column the same or two row the same, the determinant is 0. Right? And so determinant is like that. If the first one is of the right order, use 1, 2, 3, or 3, 1, 2, or 3, 1, or 2, 3, 1, that is still the same. So as long as you are choosing the proper rotation, that will give you the determinant. But if you interchange the two, if this is 2, this is 1, then that obviously give you the minus of the determinant, because you can always interchange the order back, and then you then change the index back, then the epsilon would introduce a negative sign. Okay, then you see that if you sum over this is like that. If so, this object is like that, but assuming you have alpha prime beta delta of the right cyclic order. If alpha prime beta gamma is 1, 2, 3, this is 1, then this is this one, and this is a determinant, because this mu delta epsilon is also in the right. Okay, and if this is not in the right or in the reverse order, say like in the just interchange to, so instead 1, 2, 3, you have 2, 1, 3. 2, 1, 3 will give you a negative sign. Then you sum over that. Just like here, you have two in reverse 1 of 2. Then this sum will give you a negative determinant, and this is by this epsilon you get a negative determinant. So this is exactly this expression is just like this one. After you're thinking, if two of them are the same, say alpha, if mu and delta is the same, so this will give you 0, right? But that summation will also give you 0. If say like if mu delta is 0, means the same means like alpha and beta is the same, then that will give you 0. It's like the two column is the same, that will give you 0. Determinant will be 0. So so that is, okay, exchange this to this one. So so finally we have a determinant A. We're getting close. We just need to write the rest alpha prime beta gamma. Oh, you have an A. You have the A. Let's write down the A. It's A alpha mu, and you have a epsilon alpha prime beta gamma, and B and you have another epsilon. You have this epsilon mu delta epsilon. You have this one, and then you have B delta C epsilon. Well, no. This is this one, so you actually don't have this one. This is already gone. This is changed with this. This one is this one. Okay, so now you look at this. This is just like this one. This is just like this one. And, this is sum over delta, sum of mu, and then have the index A, index mu. So this is just like A times A transformation matrix, and then the vector A mu. Okay, so this is just like that. And now this transformation property is it's like a vector. It's like this one. It's like a transformation of a vector, but with this determinant vector. So this transform like a pseudo vector rather than a vector. The cause product transform like a pseudo vector. So this is what Jackson has 6147. So basically, after you identify this, this is equals to that, and this relationship, you just focus on this relationship. This is like also like a transformation. If A is the transformation matrix, then because it is either 1 or -1, you can change it to the other side. Then this is how the epsilon transform. It transform using 3 identity matrix multiplied by a epsilon in the original frame, which basically transform the original frame to the original frame in alpha prime beta gamma, alpha prime beta gamma to the mu delta epsilon space. So transform to this. And so this is just like this instead of a third rank. So epsilon transform like a pseudo tensor. Just look at this one. Epsilon just transform like a pseudo tensor. It still keep the same property that if it is in order, cyclic order is 1. In our order is reverse order is -1. If 2 of them the same, then it's 0. So it still keeping that, but in any frame is like that. But this also have the property that it transforms like a third rank pseudo tensor. Okay, so that is actually another check why the original one is okay, because if this is a vector, this is a vector, this is a pseudo tensor, and you sum over 2 indices beta and gamma. This is what in tensor notation we call it a contraction. We contract 2 of the indices. And the third rank tensor with 2 vectors, you contract to another vector. But this is pseudo vector. So after the contraction, this becomes a pseudo vector. Okay, so it's always like that. But obviously, if one of them is a pseudo vector already, and do that kind of contraction, that you go back to a tensor, go back to a vector. So you 2 of the pseudo object add together, it comes back to ordinary object. Okay, and so that is the difference transformation. So originally you don't have this determinant A. So if determinant A is always 1, just you always consider just rotation, then the vector and pseudo vector doesn't matter. It's just everything transformed the same. You can say they are the same object, but if you include the improper rotation or spatial inversion, then vector and pseudo vector, they transform differently. So you can extend pseudo vector to pseudo tensor, second rank and third rank, or any rank, or even rank 0 in the scalar. You can have a pseudo scalar also. If you have a pseudo scalar, then you do a spatial inversion, then obviously it change sign. Pseudo scalar will change sign. And one example of pseudoscalar is like that. So if this is a pseudo vector, you do a dot product with a vector is A dot into D dot into A, If D is also a vector, this is a pseudo vector, then obviously this is scalar, but this is a pseudo scalar. This is D dot in the B code C. An object like that is a pseudo scalar. We can define it as pseudo object in different rank. Okay, so that is that. And so this is a differentiate the Hall transformation of vector and pseudo vector. An example of vector in space, an example of an improper transformation is version. And then you can look at example. Okay, so this is all done. One example is like you do a spatial inversion. You can inverse one axis or all three axes. So we have a vector, homogeneous vector x. If you do inverse x, y, z into minus x minus y minus z, or basically change the coordinate. Origin is pointing this way. If you change your x prime is pointing to negative 1, y prime points to negative 1. So that is total spatial inversion in all direction. Then this vector in this new coordinate system will change sign. This is the original vector, right? And the x prime will be equals to minus x. In terms of coordinate, this is I should actually say this is not equals. This is transformed to. This is a transformation, or x goes to negative. Right. So that's so if you do a total spatial transformation, so you require that all the position vector will have a negative sign. And there's some table, a table 6.1, we talk about all this. If you just look at spatial inversion part, and like x will be in spatial inversion, it will have a negative sign, so it's called odd or vector. And but there are other quantity like the angular momentum involve a cross product x cos p. Both satisfy this odd vector, and this becomes a pseudo vector because x is a vector, p is a pseudo vector, and both transform like that. So you this because of this both have a negative sign. They transform to something without the sign. Then this is how a pseudo vector transform, or call it Jackson also call it even under the spatial inversion is even, right? So there Jackson listed up a bunch of quantity, both in mechanics and E&M. So in E&M, obviously, electric field, you can say electric field is under inversion. Electric field change to minus 1, right? You do a spatial inversion, you introduce a minus sign. I forgot the minus sign. But magnetic field will not have a minus sign. Magnetic field is even, electric field is odd. Okay. You can look using some of the physical law that we derived so far, say like the Faraday's law. We have partial B, partial T is minus curl of E, right? And we'll stay with just spatial inversion. Then E is a vector, and this is like a cross product. And gradient actually transform like a vector because X is transformed like a vector. So the cross product between this one are actually a curl, but it's like a cross product. We still have the same epsilon. Then this dB dt will be a pseudo vector, and then B is also a pseudo vector. Okay, so B will, under this inversion, we change to positive. It's not, doesn't change, the sign doesn't change. Okay. Okay, so B is pseudo vector, and likewise, there's something that related to that, the X field, obviously, and then the magnetization. But then if you have a pseudo vector, say E cos into B, is proportional to this, the S is proportional, the Poynting vector is proportional to that. There's a mu in here. It's E cos X, so it's mu. Depends on what medium, but this is vector, this is pseudo vector, but there's a cross product. So cross product, and then with a pseudo vector already, this becomes a vector again. So S is transformed like a vector. Okay, so that's the spatial inversion, and that consideration is the same as what we did before. What we did the transformation matrix, because the transformation of this one is just basically the transformation matrix of spatial inversion is just quite obviously. You just X change the minus X, Y change the minus I, so you have minus 1. This is a special case of an improper transformation. The determinant is obviously minus 1, right? And so X prime, Y prime, Z prime will be equals to this minus X, Y, Z, right? The rest is 0. Right. This is this transformation, and so that will satisfy the transformation without the determinant sign. But if you have vector that actually doesn't change with this one, so you add the determinant that, if you have a magnetic field, that should have a minus sign, so you have dx prime, dy prime, dc prime will be, you need to add the minus 1 factor. This the determinant of A, and then this matrix times dx dy. If B is a pseudo vector, then obviously this multiplication will give you a minus sign, basically a minus sign, and then multiply by another minus sign, become positive again. So a pseudo vector transform like that under spatial inversion. Okay, so that so far that's all the discussion. I mean, sometimes we are not transforming all three. Sometimes we talk about the spatial inversion, just one of them, but it's still the same. But in that case, you don't have that because you're mixing the coordinates. So if this is just changing X, then this is still 1. This is still 1. This is still 1. This is still 1. So under this this inversion in just one of the coordinate, then obviously Bx doesn't change because of minus sign times the minus sign. But By change the negative sign, Bc change the negative sign. Okay, so you need to separate the two cases. One is a all three coordinate change sign. That's a total spatial inversion. But if it's just one coordinate, then you're mixing the components, so you don't have that odd and even kind of differentiation, but you still can separate vector and pseudo vector by this definition, whether you have a determinant, whether it's a one and minus one in front of the transformation. Okay, so yeah, it's good.